Hi guys, welcome to your Unit 6 Lesson 4 notes on scientific notation. By the end of the day, you'll be able to express numbers in scientific notation. So what we're going to do is we're going to look at 3 numbers and see if we can figure out what the pattern is. So these numbers are already in scientific notation, you can tell, because you've got some number times a power of 10. Okay, so when we look at this, I notice first we've got a positive 2 for our exponent, and I notice that we're multiplying times 100, because that's what 10 squared is. 10 squared is 100. And what we did with the decimal point is we took our decimal point, and now instead of being over here, it goes from here, and I'm going the opposite way. We took our 5, and our decimal point went 1, 2, to go over there. So again, over here, our decimal point went 1, 2, like that. So our decimal point, if we take this movement that it just took, that represents a movement of 2 to the right. So it went 2 places, 2 places to the right, that way. So that's a positive 2, 2 places to the right. Now let's look at this guy. We've got another positive exponent up here. That's a positive 4. And when we multiply times 10 to the 4th, which is 10,000, also notice this 4. There's 1, 2, 3, 4 zeros. That's no coincidence. Anyway, so we got a positive 4. So we're going to take our decimal point right here, and we're going to move it 1, 2, 3, 4 places to the left. And that's where our decimal point ends up over here. It started here, and 1, 2, 3, 4, and by the left, I totally mean right. So this movement takes our decimal point and moves 4 to the right. So far we've got positive exponents. We're moving to the right. Let's look at this guy. What happens if we take a power of 10, but this time we've got a negative? This time we've got a negative exponent. What are we going to do with that? 10 to the negative 1 is 0.1, 1/10. You'll remember from negative exponents to take 10 to the negative 1. That's the same thing as 1 over 10 to the first power, which is 1/10. And that's exactly what this is. That's 1/10, but in decimal form. Now, where does our decimal point go? Well, it used to be right here, but we move our decimal point 1 to the left. It used to be over here, and it moved 1 to the left. So this represents a movement of moves. Well, maybe I should spell moves correctly. Moves 1 to the left. And that's going to be the pattern that we find. When we have a positive exponent, we move the decimal point that many places to the right. And when you have a negative exponent, you're going to move the decimal point that many places to the left. So here we go. If the exponent is positive, move the decimal point to the right. And if the decimal point is, if the exponent is negative, move the decimal point to the left. Let's draw some symbols to help us remember. I'm going to draw a plus sign with an arrow going through it to the right. And then I'm going to draw a negative sign with an arrow going through it to the left. And these symbols are going to help us remember what direction to move our decimal point. So let's do some examples. All right. So here, we know that 2 megabytes is equal to 2 times 10 to the 6th power of bytes. Well, how many bytes is that really? Let's look at our exponent. We've got an exponent of 6, which means we're going to take our decimal point and move him to the right 6 places. So we'll start out with our 2, and our decimal point started out here, but needs to move 6 places to the right. 1, 2, 3, 4, 5, 6. It's going to end up right there. So I'm actually going to get rid of him, put him right here. And if our decimal point is there, then we need to fill in a bunch of zeros. 1, 2, 3, 4, 5, 6 zeros. And of course, as you remember from elementary school, you need to fill in commas every 3. When you look at that number, what is that number? That's 2 million. 2 megabytes is 2 million bytes. That's a lot of bytes. It's a lot of memory. Anyway, we can talk about what that really means in a little bit, but there we did. 6 places to the right. You'll also notice that since it's 6, there's 6 zeros. That's a cheat sheet way to remember that. So, but that only works with positive exponents, because look at what happens when we have a negative exponent. A nanosecond, nano like 9, like 9. Mega is like million, so that's where that comes from. Fun fact, that's why it's 2 million. Okay, 8 nanoseconds means we're going to take 8 to the 10 to the 8 times 10 to the negative 9th, and that'll give us what fraction of a second that is. So we'll start with our 8. But since we have a negative exponent, negative means we're going to move 9 to the left. We're going to move that decimal point 9 places to the left. Let's go ahead and take our decimal point, which started out here. It needs to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Those were not evenly spaced. Oh well. So our decimal point is here, which means we have 0.1, 2, 3, 4, 5, 6, 7, 8 zeros this time. So the exponent doesn't always tell you how many zeros there are, unless you want to count the one before the decimal point. That's why I want to emphasize the movement. It's moving 9 places to the left. So there you go. 8 nanoseconds is 8,000 million trillionths of a second. Anyway, it's 0.008. Okay. Now let's see. You got it? Use your shortcuts to help you with C and D. With C, we see that this is a positive 3. So we're going to take our 1.6 kilometers. And we're going to move our decimal point 3 places to the right. So here we go. 1, 2, 3. Our new decimal point is right here. Don't need you. And we're going to fill in with zeros. Oh, we moved it 3 places to the right, but we don't have 3 zeros anymore. We only have 2 zeros. That's because this 6 is substituting for a 0. So 1.6 kilometers is 1,600 meters. Oh, I haven't been filling in our units, you guys. Bytes, seconds, meters. 1,600 meters is just shy of a mile. Fun fact. Okay, since we had a positive 3, we move to the right 3 places. And look here, we don't have a positive 3, we have a negative 3. Looking at our negative shortcut, that means we are going to move our decimal place to the left 3 places. So we start out with our 3. Our decimal point started here, moves 1, 2, 3. Our new decimal point goes right here. Let's put a 0 in front of it and fill in 0.003 seconds. So a millisecond is 1,000th of a second. Also, a kilometer is 1,000 meters. That's why they're both 10 cubed, because thousands. Isn't that great? Well, why is this helpful? Well, when we're working with really, really large numbers like 36 million, or really, really small numbers like 0.0005, that's obnoxious. Look at all those zeros. Gross. That takes up a lot of space. You have to count out how many zeros do you have. So instead, we use shortcut. We use scientific notation because scientists use this a lot. So what scientific notation means is you're going to take a number, if it's, scientific notation, nice. You're going to take a number and you're going to express it times 10 to the nth power. So whatever number you have, you're going to multiply it times 10 to something. Okay. So that means you need A needs to be between 1 and 10. It can be equal to 1, and that's great. So yay, A can be 1, but it cannot be 10. So it's A is greater than or equal to 1, but it's less than 10. Oops. And n has to be an integer, which means you can't have like a half power or anything. Remember that integers are numbers like -3, -2, -1, 0, 1, 2, 3, etc. Okay, so when you see scientific notation, think something times 10 to a power. You know what? I'm just gonna make this black. So here's how to write a number in scientific notation. I'm going to do one for you, and then we'll look at our steps, and then we'll do another one. You know what? Let's just take the numbers that that I dealt with, right? So here, okay, let's start it with 36,600,000. The very first thing I want to do is I want to take my decimal point and move it to the first non-zero digit. So my decimal point started out here. I'm going to count how many steps it takes to get there. That's 1, 2, 3, 4, 5, 6, 7. That was 7 moves, 7 places to the right. So the very first thing I did was I moved the decimal point to be after the first non-zero digit. There's only one, okay? So I moved the decimal point to be after the first non-zero digit. Non-zero meaning it's not 0. Okay. And then I want to count how many places I moved. We kind of already did this already. 7, we moved it 7 places. So we count the number of decimal places moved. This is going to be the power of 10. So we're going to take 10 to some power. That's what we're going to put. So here, 7, we're going to have 10 to the 7th power. So we know we have something times 10 to the 7th power because we moved it 7 places. Now, when the number is greater than 1, the exponent is going to be positive. That means this number. If your starting number is greater than 1, your exponent is going to be positive. But we know this already because we have our fun shortcut, right? We moved our decimal point. Well, I guess I kind of did this kind of backwards, huh? This is to go the other way, so never mind. But, okay. Or should I have explained this the other way? Oh, well, we're going to go with it. It's positive. So forgetting all the zeros, we're just going to leave those alone. What number are we left with? We've got 3.96. So putting this number in scientific notation gives us 3.96 times 10 to the positive 7. Now here you can tell we've got some number A, and A is between 1 and 10, right? 3 is certainly between 1 and 10. There you go. So we did it. Oh, I forgot the last blank. Okay. If the number is between 0 and 1, the exponent of 10 is negative. So here we've got a number that's greater than 1, so exponent gives positive. Here we've got a number that's between 0 and 1, so our exponent is going to be negative. So let's do this one. First, we need to move the decimal place to be after the first non-zero digit. Did not realize I was hiding. And by hiding, I mean highlighting. Okay, so it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. That was a move of 9 places. Oh, hey, look, we counted. That's our power of 10. Nice. So we know we're going to have 10 to the 9th power, but it's going to be negative because this number is between 0 and 1. So it gives us 10 to the, 10 to the negative 9th power. And what number are we dealing with? Well, this is just a 5. So it's going to be 5 times 10 to the negative 9th. There we have it. There's your scientific notation. Cool. Now that's great, but what happens if we have 2 numbers and we need to multiply them together? Well, let's do the same thing. I'll do one, I'll explain the steps to you, and then you'll take it. Okay, so when I look at this, I see 2 kinds of numbers. I see our between 1 and 10s, and then I see our powers of 10. So I'm going to group them accordingly. According to the commutative property of multiplication, I can take 1.5 times 10 to the 4th times 3 times 10 to the 9th, and I can rearrange these 2. I can move them, can reorder them, and then multiply it that way. And that's exactly what I'm going to do. I'm going to take 10 to the 4th. I'm going to move him. Take 3 there, 10 to the 4th there. Why did I do that? I did that so that I can multiply 1.5 times 3, and then I can multiply 10 to the 4th times 10 to the 9th. In fact, I want to do those first. Because when I look at 10 to the 4th times 10 to the 9th, I see that as multiplying my powers together. I both have bases of 10, so I can just add their exponents together. 10 to the 4 plus 9th power. So there you go. That's the yellow side first. Now let's do the blue side first. Second. 1.5 times 3 is 4.5. Ta-da! Okay, now we're almost there. We're almost done with our scientific notation. We just take everything down again. Well, 4.5 times 10 to the 4 plus 9 is 13. So we have 4.5 times 10 to the 13th power. Isn't that great? So what did we do here? The first thing we did in this step was we grouped the terms by the base. That is, we want to get the powers of 10 together. Then we multiplied them together, making sure to spell multiply correctly. Multiply. And then after that, we just wrote in scientific notation. So there you go. There's your 3 steps. Now take those steps and apply them. So our first step here is to group the terms by base. So I'm going to take, again, my powers of 10. I want to make sure those are together. And then my just other numbers, I'm going to put them together here. So here when we do this, we're going to get 6 times 4 first times 10. Can I skip a step? Can I do them together? No, I won't. I'm gonna write out every single step for you guys. Okay? We've got our front numbers out in front. We've got our powers of 10 out in the back. 6 times 4 is 24 times 10 to the 3 plus 5th power gives us 24 times 10 to the 8th power. Uh-oh. But guys, look at this 24. Remember, in our scientific notation notes, it needs to be between 1 and 10. And 24 is bigger than 10. That's not allowed. So because we have that happening, we actually need to do one more scientific notation move. We need to take this decimal point and we need to move him one more space. Move this up here. So that means we're going to add 1 to our exponents. Crazy, huh? Because we move 1 to the left. That's 1 more power of 10. So we actually get, after moving our decimal point, 2.4 times 10, and then we add these exponents together. 10 to the 9th power. Okay, cool, but why are we doing this? Why does this make our life easier? Well, let's say that you're working in your job and you're working with these big numbers. You're working with 6 times 10 to the third, so 6 times 10 to the third is 1, 2, 3. Okay, and then you're also working with 4 times 10 to the fifth. 1, 2, 3, 4, 5. So you need to figure out what is 6,000 times 400,000. And it's tough to try to do that and keep track of all those zeros. What happens if you lose a zero along the way? Then you might end up paying, if you have to, let's say you buy 6,000 of things that are worth $400,000. Probably the other way around. You're going to buy $400,000, 400,000 things of things that cost $6,000. Yeah, nice. Like cheap cars or a really expensive bicycle. Anyway, so you need to buy 400,000 of these $600,000 things for your company. And what if you miss a zero? Or what if you overpay? What if you pay 10 times as much as you should? That's no good. So to try to figure out what that is, that's gross, but it's a lot easier to keep track of them with scientific notation. So scientific notation is only here to make your life easier, I promise. Let's do one more. This time, instead of multiplication, we're going to divide. So let's take this multiply. Let's say, just kidding, we're not multiplying. We're going to divide here. Same process though. Okay, here we do. We're going to group our terms by the base. So we're going to take our front numbers and our powers of 10. We're going to split them up. So it's the same thing as 4.8 divided by 1.6 times 10 cubed over 10 to the first power. Now 4.8 divided by 1.6. That's just 3. That worked out really nice. So that's cool. Got our front numbers here. Powers of 10 here. Now remember, when we're dividing with powers, that's the same thing. This dividey guy right here turns into a minus guy in our subtraction of our exponents here. So we take our exponents, we subtract the top minus the bottom. 3 minus 1. 3 minus 1 is 2, so that's 10 squared. That gives us an answer of 3 times 10 to the second power, which is 300, so that's fun. Okay. So this whole thing right here, that's equal to 300. Yay, but I asked for an answer in scientific notation, so here's the answer in scientific notation. All right, guys, what's important to remember about scientific notation is that your first number times a power of 10, your first number cannot be 10 or bigger. It needs to be between 1 and 10. Yeah. And let me know if you have questions, and I hope you have a wonderful time on your homework. And remember, guys, keep it positive.